We have more materials at our disposal than any civilization before us ever had. If you go back 200 years in human history, we basically built civilization on three elements. Carbon, in the form of wood and coal later. Calcium, which is cement and structural materials for buildings. And then iron. And iron, of course, was the dominant feature because iron supplanted bronze and before that stones. And so for many hundreds of years, that was what human civilizations were built on. In the last 100 years, we've gone from 3 elements to 70. So now we use rubidium, tungsten, lots of rare earth metals, all these obscure components that basically allow us to either fine-tune the structural properties of a material, to fine-tune the surface properties so that it gets more reflective, or to fine-tune the absorption. So a lot of the sensors and the electronics that we've created are basically changes in the electrical and optical behavior of materials. That has become incredibly powerful. Add to that now that Moore's law has given us enough processing power that we can actually computationally model materials without making them. So we can begin to explore not just an individual material, but combinations of thousands of different types of materials, whether that's in biology for synthesis of new kinds of biological pathways, so whether that's in structural materials to model the interactions, or whether that's in process chemistries. So if I take a look at gold recovery and gold recycling, it used to be done in a process that's known since Roman times by soaking the gold in an acid bath, very toxic, lots of fumes come out, you dissolve the gold, aqua regia. But today we can actually computationally model chemistry options that allow you to do the same process in a water bath at room temperature with iodine and very simple chemicals that you can actually safely drink, no acid involved. And the process is more efficient that way because I basically fine-tune the chemistry to extract just the gold out of the electronics I'm trying to recycle. The same is true for structural applications. So today's wind turbines are no longer just big pieces of wood or trees sliced up the way they used to be when the Dutch first developed windmills. They are very high-tech blades made of carbon fiber with specific tuning, with nanoscale materials embedded in them for strength and for particular vibration dampening performance. And so it's that kind of fine-tuning of an airplane wing, a car door, or the battery materials to be absorbed as much charge as possible and to give it back with very high efficiency. That's what's unleashing this materials revolution. And it has not only a massive performance impact because we can tune the material to have exactly the performance characteristics we want, but it can also reduce the environmental footprint, whether it's in the form of the water, the energy, the temperature required, or just how much weight, how much of the material itself we need. And it can improve the ability to reuse it because if we tailor the material to be easy to disassemble and to reprocess, we can actually reuse the same material infinitely, as opposed to many of our historical materials which are once through.